As always, the views expressed during today's webinar are those of the speakers, not of Stratford, the speaker's firms, or clients, and are not intended to provide legal or tax advice. We have gathered a panel to provide insight to counsel for Medicare and Medicaid providers on how to effectively evaluate and potentially challenge overpayment sampling and extrapolations in provider audits. Our panel today includes Dr. Patricia Maykuth, President of Research Design Associates, and she's joined by David Ross, attorney at O'Connell and Aronowitz. Speakers, when you're ready, we'll get started. David, I'll hand over to you.
Thank you, Colin. Welcome, everyone. We're going to be starting out with a little primer on the legal issues involved in statistical sampling and extrapolation. And then we're going to cover a lot of concepts, key concepts in detail when Dr. Maykuth begins her presentation. So that being said, we're off. So what is sampling? Well, sampling is taking a subset of the claims in a Medicare or Medicaid provider's universe of claims, and these are the claims that the auditor is going to audit for potential disallowance. And what's key is how this sample is chosen. And more often than not, it's chosen via computer software, which generates what are called pseudo-random numbers. Now, they're not truly random numbers. They're pseudo-random because they're derived from a formula that the computer program uses when a seed is input into that program. And this is a replicable process, so every time the program is run with the same seed, it will produce the same set of pseudo-random numbers, hence the name pseudo-random. But for all intents and purposes, the numbers are, in fact, random for our purposes and for the purposes of statistics. So in order to be valid, the sample must be randomly selected. Now, just because it's a random sample doesn't mean it's a valid sample. There are some very interesting aspects to this, which Dr. Maykuth will touch on. But the sample itself, while randomly drawn, could be biased or otherwise not representative, therefore not a valid sample for purposes of the audit. What is extrapolation? This is when you take the results of an audited sample of claims and project onto the universe of claims the total dollar amount of overpayments, which the audit will be seeking from the provider. So the sample has a known amount of dollars in error, assuming the audit was done correctly, and the claims were correctly evaluated. And then this is projected onto the claims universe with a given level of confidence, called a confidence interval. And that's what is needed here because it's not an exact dollar amount, it's an estimation. And with any estimation, there's a plus or a minus. So the confidence interval will give you those pluses and minuses of the range. So a lot of clients object to this and they say, how can they do that? This is not fair. Well, it's a widely accepted approach. It's called sample estimation, sampling, extrapolation, whatever term you want to use. Sample adjudication is another term. So basing the whole outcome really on the outcome of the sample. So if it's done properly in accordance with statistically valid methods and procedures, it is widely accepted by the courts. That being said, the auditors have to follow statistical rules. And this process has been used by the federal government as early as 1972, and that's from the Chavez case, may even be earlier. And it's now codified in the CFR, 45 CFR 160.536A, and says that the secretary may introduce the results of a sampling study, and if it's based on appropriate sampling and computed by valid statistical methods, constitutes prima facie evidence. Now, the provider, in turn, has the burden to produce evidence reasonably calculated to rebut the findings of the statistical sampling study. And thereafter, the auditors are given the opportunity to rebut the rebutted evidence. So state Medicaid programs generally use a similar approach. And if you're really interested in the evolution of this and the history, you're welcome to read the Chavez case. And also HCFA Revenue Ruling 86-1, which is probably the earliest proclamation of this policy. And HCFA, of course, Healthcare Financing Administration, prior name of CMS. So Medicare and the MPIN. What is the Medicare Program Integrity Manual? Well, it is a rule book. And Chapter 8, Section 8.44 governs statistical sampling and extrapolation. And this is really the handbook. It's been around for quite a while. It was recently modified via Transmittal 828, which was effective January 2nd, 2019. And there are a lot of interesting things in this transmittal, and it highlights the changes, tracks them that were being made to the existing MPIM at the time. Pretty interesting reading. And one of the key changes, which was effective in January 2019, is that the auditor need not extrapolate the results from the sample audit to the universe of claims if the error rate is below 50%. Now, this doesn't say that they are precluded from extrapolating. It just provides a scenario where they have that option. And there are other conditions which allow them to continue to extrapolate despite the error rate. But that's a more complex concept that I'm trying to convey at this point. And that's been a significant change. And we've had one case where the outcome was positively affected by this change in the MPIM. So it was great news. Another factor that's recently been on the landscape is that the auditors themselves have been audited by none other than the OIG, the Office of the Inspector General. And this audit was how the Medicare contractors handle appeals within the Medicare program. Came out last month. If anybody wants a copy, please shoot me an email and I'll send it to you. But it was a fascinating study that concluded that the Medicare contractors were inconsistent in how they interpreted this revised MPIM. And there were 8 procedures that were not uniformly carried out by these Medicare contractors. So the study has some value. It wasn't exhaustive. It did not look at the entire universe of Medicare audits, but picked some. And it's very interesting that there's some variation out there, and that CMS has responded to this audit and indicated that they will work to improve, to streamline and eliminate any disparities in how the audits are reviewed. So there's also another document, which is actually pretty interesting reading. It's the Toolkit for Medicaid Fraud Control Units. That came out in 2018. Again, send me an email if you'd like a copy of that. And it's intended to be guidance for the Medicaid Fraud Control Units, and they operate in all the states. It's an excellent primer on how audits are designed. The first example goes from start to finish, and it shows you in a lot of terms and how to really approach the problem from a design perspective. So there are limitations to this document, so it's not intended to establish formal standards or restrict the methods available to the Medicaid Fraud Control Units to complete their mission, and I'm reading from the introduction. And I'll read this verbatim. Because statistics is a broad field with a wide variety of effective and valid methods, a sample or estimate may be valid even if it does not follow the steps in this guide. So it is not a rule book where every play has to be followed in sequence, but the way it's written, I would really challenge anyone to provide a process which didn't follow the essence, the essentials of this step-by-step guide. So in that respect, it's basic, but there aren't a lot of ways to do this. So I would think if you have a Medicaid Fraud Control Unit audit that did not follow these steps or is materially different, I think you're going to have some persuasive evidence with this toolkit, despite its disclaimer. So the various states, there are no Medicaid national program rules for sampling and extrapolation. It's not like the Medicare program, which has the MPIM. There's no universal guidance. So your individual state may have simple rules, complicated rules, or no rules at all. So you're going to have to become an expert on the case law, administrative hearing decisions in your state. You want to talk to practitioners. There are a lot of nuances to this type of practice. And the burden of proof is going to be on you, the provider, to challenge the state's statistical sampling and extrapolation methods. And they're going to enjoy a presumption of validity. And until you rebut that presumption of validity, because they are the state, there may even be a rule or regulation or other guidance document which gives them that presumption of validity. You're going to have to rebut that if you want to be successful in your challenge. So here's where we really come to the most important part of any audit defense work that involves sampling and extrapolation. You just can't do it yourself. You can't evaluate a case like if it was a personal injury case or a med mal case. You'd never dream of handling a case like that without one or more experts to explain to you the various issues that are involved. It's just not something that is within our typical purview as attorneys. So you're going to really need an expert. And the expert's going to talk about the audit process that was used, the results in your particular case. They'll answer the key questions that you're going to have, hopefully as a result of this seminar or further reading. And if you don't ask all the right questions, they will ask those questions for you because they'll know what, if anything, is wrong with the audit approach that was taken. And these are absolutely critical components to your defense, both when you're responding to the audit, at the administrative stage, redetermination, reconsideration stages. And if you have to go to a hearing, you're going to need your expert to testify. So key questions are, is the audit process used by the auditors properly designed? Should it have been the way they did it? Should it have been a stratified sample? Should it have been a simple sample if it was stratified, and vice versa? Is this process suitable or appropriate for use in this audit? How was the sample size chosen? Was that proper? Was the sample tested for randomness, for unbiasedness, representativeness? Sample size adequate, large enough for the confidence interval that is being expressed by the auditors. One of the key elements of the MPIM, and we see this in federal decisions, is that providers frequently bemoan the sample size and that it's too small. It's too small. Well, you're going to need more than that in your defense to convince at least a federal judge that you have a real problem with the sampling and extrapolation that was used. It's sort of like a sliding scale. Your sample size may be smaller than ideally sought if you were doing the test yourself, but it can be big enough to come up with some confidence interval, though not necessarily the confidence interval that's been stated by the auditors. Your expert will be able to tell you, how close to the mark did they come. Also, critically important, do you have a probability sample? Dr. Maykuth will talk about the key elements of a probability sample, and did the auditors properly document the audit? Their paper trail is going to be critical because you're going to want to be able to replicate the audit. It can't be replicated. There are real issues, which we'll get to in a minute. So questions about the software program used for random number generation. Is it certified by some body, or is it otherwise widely accepted for this purpose? Is it, for example, RATstats, a free program offered by the OIG on its website? Or is it proprietary? Was it designed by someone and not necessarily certified by anyone or widely accepted by anyone other than the designer? And we had this situation here in New York. And the real question was, you know, is this software program being used in the manner it was designed to be used? And was it working the way that the expert claimed it was working? And we had an expert look at the program source code. And in that case, the testimony was that the program did not process the numbers in the way that the expert claimed it did. And it was very interesting. We never would have known that had we not had an expert look at the program source code, the actual programming lines inside the software. And if you request that source code in a proprietary software program and you're denied it, you should argue it's a violation of due process, because that software program cannot be a mystery to you or to your client, to the court. It can't be a black box. It's got to be transparent or widely accepted in the field where this would not be a productive area of inquiry because everybody knows it and everybody uses it. Like RATstats is just one example. So replication. If it can't be replicated, and I say the results, I mean the outcome, the production of the random numbers, the same claims within the frame, which is a technical term that Dr. Maykuth will explain, you have a serious problem because it is science. It's a scientific approach. The sampling extrapolation is an experiment. And we all recall our scientific method from our elementary education, that you need to do the experiment multiple times with the same result each time. That's the essence of reproducibility, replicability, whatever word you want to use. And if that can't happen in your audit, then something happened along the line that would render this to be unscientific. And as defense counsel, that's an excellent place to be with differing outcomes. Retaining the seed, that's a critical factor. Is the value that's input into the random number generator or generated by the program itself, but it must be retained regardless of whether it's user input or automatically generated, so that when you go to run it or your expert goes to run it, you can get to the same outcome. And another critical factor is the frame sorted as it was at the time the random numbers used to pick the sample were placed upon it. So for example, if you have 10,000 claim lines and you have a random sample of 258 and the second value in the sample is 143, you go to line 143, okay, that's your claim, that's your data service, that's going to be selected for audit. Do you have that frame organized in any way other than it was when the auditor applied that 143 to that frame, you're going to wind up with a different data service. So you need to have that frame sorted as it was at the time the numbers were applied to it. Another issue is stratification used. Well, this is going to involve multiple random samples. And Dr. Maykuth will talk about stratification, when it might be used. And last but not least, the extrapolation calculations themselves need to be verified by an expert. Even the Medicaid Fraud Control Unit toolkit says don't do these yourselves, have an expert calculate this for you. So here we have a colorful graphic of our favorite candidate for president of the math club, and he is pointing to an easel-based graphic, which says 21% of the boys and 30% of the girls support me. Therefore, I'll get 51% of the vote. Okay. Good idea, the right idea, but it's the wrong answer. It's not how it's going to happen. And who can forget, some of the older folks in the audience or history buffs, here is President President Truman-elect holding a newspaper which proudly proclaims his loss, Dewey. Well, what happened in this election? What happened in this prediction? Only folks with telephones were polled prior to the Chicago Daily Tribune releasing this story. And that led to a type of response bias where only people with telephones were asked. People without telephones had no input. They weren't part of the sample. They weren't part of the universe. Therefore, you got a skewed or biased outcome. So here are some things that need to be present in your case to have statistical validity. Remember, it's a science. It needs to have certain elements, be considered controlling, and a proper estimation of the repayment in your particular audit. So I've listed them all. It's sort of a summary of what I've spoken about. The first few, Dr. Makepeace will talk about, but fairly high order mathematics. Each frame of a given size will be able to have a certain number of samples of a given size, and there are formulas used to calculate that. Each member of the sample must have an equal probability of selection. And you'll see how this is important when she gets to some of her examples where there was no possibility of selection. And then you know that there's something wrong with the sample. So the goal of all of this is to, at least in the judge's eyes, is to weaken the estimation of overpayment for the universe by attacking the sampling and extrapolation. And ultimately, the goal would be to handle and deal with defending only the alleged overpayments in the sample itself. That's really a victory at the end of the tunnel of a process like this. And now you're talking about a much smaller dollar value at stake. And when you can do that, you've done an excellent job for your client. So with that, I will turn it over to our expert, Dr. Pat Makepeace.
Thank you, Mr. Ross. Good day, everyone, and thanks for joining us. I know we've all been through an awful lot of web meetings in the past 6 months, and I also know this topic is relatively dense. I apologize for both. My goal this session is to present some insights into the mechanisms of probability sampling that may enable you to ask good questions about statistics and about how to evaluate an overpayment. I firmly believe that smart, interested attorneys can grasp enough of higher-level statistics to be good consumers and good translators of those statistics. I'll get into the weeds a bit in my explanations, but it's only to give you a glimpse of what statistics can and cannot do. And while your gut instincts may not be of very much value in calculating a probability statistic, they are very useful in informing the consumption of those statistics. I hope your takeaway today will be a real feel for what does and doesn't seem right, and an improved sense of what questions to ask about audits and voluntary repayments. There are also a list of terms associated with this presentation, so that you can follow along with them and help decode some of the jargon. Mr. Ross has opened with some examples that should raise skepticism about what questions statistics can answer. And I'll try and give you a feel for how to use statistics to improve decision-making, but with a clear eye to the view of the limitations of those answers. You can't You can't predict who's going to be president, but if you have the right people show up at the polls, you can have a likelihood of who might be president. But Dewey was not president. And relative to the birth date of a baby, the due date of a baby, you can't predict one event statistically, so you have to use a sample, say maybe of 20. But in order to know the answer to that question, you need to know the date of conception, and that a full term for a baby is 280 days. You also need to know that only 40% of babies are born exactly on that 280 days. You don't know the distribution, so you can't calculate a confidence level. And with all this lack of knowledge, the best you can say is plus or minus a week. So within a 2-week interval, you'll have an estimate of when the specific child might be born. And you also don't know the dollar amount of overpayment. Statistics can tell you how likely the mean of the sample is to represent the true mean of the frame from which it was chosen. It can't tell you anything more or less than that. Bad samples don't even do that well. It's just an exercise in arithmetic and not probability statistics. As consumers of statistics, we have to be careful not to be intellectually lazy, and it's hard in an election year because we get all sorts of noise and all sorts of input about pet questions and mistakes and errors and intentional misleading. And it's unfortunate, but a good fortune teller with a few bits of information can give the impression of an answer with a high degree of confidence and accuracy, and might not be any better than a poll. This is our roadmap, and we're going to follow it left to right as though you're reading, and then down in the lines. The first thing you see there is a history of prior error, and you'll find that in the MPIM. And all probability statistics need a start point. You're familiar with a random sample needing a seed to start with. The prior history of overpayment error is necessary in order to start this probability process. You either know it, you invent it, and I hear folks say, well, it's not required, so we don't have to have it. Well, maybe your regs don't require it, but statistics does. You've got your universe, which is the dollar amount of claims paid to the provider in a specific time frame. And you add to that what you want to audit, the who, what, when, and that gets your universe limiting criteria to take you to the frame. The frame or sampling frame is a subset of the universe defined by those universe limiting factors such as codes, departments, maybe providers, sites, and any number of things you might choose to include or exclude. You often see railroad employees removed because they have a different system than Medicare to take care of their needs. So the idea is to take an extrapolation from the sample that will yield an accurate estimate of what the true overpayment in the frame would have been if you had audited every claim. So once you get your frame set up, then you make an arithmetic definition of it. It's not a word definition, but there will be a word definition, but you need to know how the numbers array. From that, you can choose the right inferential statistic and method, and then you have to follow the rules of that statistic and that method. It takes you then to our next line, where you have the chosen methodology. The two most common are simple and stratified here. Then you calculate your sample size and go into the random process that David has just described, where you select a seed, you create a table of random numbers, and you apply it to an unbiased file that is sorted in the way it was when the sample was chosen. That gets you to the calculation page. You have because you're using, in this case, point estimates and confidence levels, you need these four things: independent observations that are randomly selected, normally distributed and representative. That allows you to go on to select a probability sample, and all of this has to be done before you go into the field to audit claims. It's important that you understand that once that sample is selected in the middle of the second line, Nothing in front of it can get changed. Otherwise, you've got to go back to the beginning and redefine things. But if you get into trouble after the random sample, it's too late. Sampling units is what is measured: the claim line, the claim, the beneficiary, the provider. But it can be any of those in the beginning, but it must stay the very same thing throughout the audit. You can't change from one to another. The sample is a randomly selected subset of the sampling frame that is used to be audited for overpayments or underpayments. We're going to stay with an example here for several slides, and that is a universe of 10,000 claims, a frame of 100 claims, and a sample of 5 claims. So you use your audit definition to limit your sample from 10,000 to 100. And then you see in your universe you had all sorts of things that could have been selected. Then you go on to your frame, which is all claims for a particular time frame and a code. And then from your frame of 100, you pick a sample of 5, and these sampling units are those 5 claims. Those sampling units have to be in the frame. They have to be in the universe. You can get a corrupted universe. Sometimes, if the sampling unit is not precisely defined or the audit definition is not faithfully executed, either of these problems can give real problems and impact the extrapolation. We sometimes see a conflation between claim lines and claims, and recently I saw a sampling unit that started out to be a beneficiary and ended up to be a claim line, and that was pretty tricky. You will see dates outside the audit definition, CPT codes that are not included, even providers not in the definition. Each of these destroys the capacity to extrapolate, and for a claim to be used in an extrapolation, it must appear in the universe, the frame, and the audit definition. Obviously, a non-existent claim cannot be randomly sampled. I'm going to get into the weeds here for a bit. Numbers are different from probability statistics, and you can be pretty good at math and intuitively estimate, calculate ballpark numbers, and be pretty darn accurate. And there are a couple of concepts, these two, that make a huge difference. A probability space is a mathematical structure of a probability model, in this case the frame, that includes all possible samples of a given size from the size of that frame from a family of events which are claims. Try and put that into English. The probability space is a precisely defined large box of likelihoods that must be understood and calculated. Probability likelihood of selection can be assigned to each claim. 2 requirements have to be there. You must be able to calculate the number of samples of a given size that can be taken from the frame of a given size. Both of those have to be constant. And then you have to know the likelihood of selection of each of those sampling units. And in a simple sample, it will be equal probability of selection. And in a stratified sample, you take a simple sample within each stratum. So here we have our frame of 100 with 5 samples. And we want, if the number of samples of 5 can be numerous. You've got 1, 2, 3, 4, 5. That's one possible random selection. 2, 3, 4, 5, 6. 1, 11, 21, 31, 41. 1, 12, 23, 34, 45, etc. What can't happen is the last one, where you have 1, 2, 3, 4, and X, and something shows up in the sample that's not in the frame. It cannot happen. There is no probability of selection for something to show up like that. So now we ask how many samples of 5 can be taken from our frame of 100. Here's our frame of 100 oranges. Now we have a sample of 5 oranges. Oops, we got a problem. We got an apple in there. How'd that apple get in there? Well, it can't get there, but it is there. So there's our apple in our sample of 5. How much difference can one apple make? Into the weeds for a good dive here. How many samples of 5, taken 5 at a time, are there in a frame of 100? We're talking about combinations. And in words, it's 1 factorial divided by 5 factorial times 95 factorial. And the answer of 5 in 100 is 75,287,520. That's how many possible samples of 5 there are in a frame of 100. Now, if you just change the frame size by 1, it drops to 71 million. If you add 1 more, it goes to 79 million. So your probability space is huge, even for a frame that's this small and a sample that's this small. So I'm going to continue with combinations here. You have a different sample size, but the frame stays the same. So same combinations formula. If the sample, we know the number of samples of 5, that's the 75 million number, 2 commas. How many samples of 2 can be taken from a frame of 100? Well, there are 4,950 combinations there. How many samples of 10 can be taken from 100? Well, there are 17,331,000,000, and so on and so on and so on. But you have 4 commas there, and you can see whenever you get into a frame size of 10,000 and a sample size of 150, you've got there are no words for those kinds, and you just start counting the number of commas. Is the easiest way that I can make sense out of it. So what is the solution to the apple? If you remember, back to my slides. There are, we'll do the first 2 first. If you go to a frame of 100, there can only be oranges. If you've got apples in there, you've got to go back into the frame and dig out the apples. The second thing you can do is redefine the frame to include apples and oranges in your sampling frame. But you may really not want to know about apples. Maybe you don't want to know about Provider Jones. You just want to know about Provider Sanchez. So you have to decide if that is even appropriate. And then, if you remember, you can go back to the sampling space, and I'm going to remember this slide of all the other, over under the universe, we selected 1 tower, but there are all those other towers. You can redefine your frame and pull out different things. But said and done, whatever is in your frame, something that's not in your frame cannot just appear. Going back to my all right, so you have those 3 alternatives. What you do find, however, is that's not what folks are willing to do. These are fallacies. There are no fixes once you've gone past the random sample to going back, redesigning, and picking a random sample of a legitimate frame. We got into the weeds a little bit about the probability space. These are actual answers that reviewers or auditors have made in writing that point out an astounding lack of understanding. All you have to do is take the apple out. Well, there are 2 problems with that. One is the sample size goes down to 4, and the other is the frame size goes down to 99. Now, seeing the impact of each of those separately, you have a good idea of how big the impact is going to be if they're both combined together. It doesn't solve the problem because you still don't know how many apples there are in the frame that shouldn't be there. The second is to assert its auditor error, and I have seen this more often than I like to admit, where the person in charge of doing the statistics says, this isn't my problem, it's not a statistical problem, it's a clerical problem. Well, if it impacts the probability space, it is a statistical problem, and it becomes, you cannot abdicate responsibility for that. I sometimes hear from reviewers, well, the ZPIC or the auditor didn't give us the data to test this, so we assume it's as they said. That's another unacceptable answer. 3 and 4 kind of go together. And the one suggestion is if you take the amount of overpayment of the apple in the sample, and you just take that and make it a 0, it drops the number of claims in error because that claim will no longer be in error. And that's in the provider's favor because it reduces the dollar amount in the sample and in the extrapolation. Well, this is a problem of conflating probability statistics with arithmetic. And while the argument might have arithmetic logic and can be explained with some ease, there is no sample of 5 oranges in that probability space. If an apple appears in there, and no telling how many apples are in the frame, you do not have a probability space. And by definition, there are no apples in the frame. It breaks all the rules of extrapolation. And when an extrapolation is corrupted, it is never in the provider's favor. No extrapolation or extrapolation without a probability sample is never acceptable, and it costs the providers multiple thousands of dollars. The last two, there is no equal probability of selection of something that's not there. You can't be picked in a sample of oranges if you're an apple, and it's just a mathematical impossibility. And if there is a 0 claim that's still included in the sample, it may not be extrapolated over. You can't add and subtract in probability statistics. That doesn't handle the probability space. So these examples are clear fallacies used by auditors and reviewers that simply miss the point of probability statistics. Probability stats are not arithmetic. When I think of this, I'm reminded of the high school student who was just in his zoomed out statistics class, and he really wasn't particularly engaged, and he got called on. And the question on the screen was, what is a probability in 1 in 5 million? And the student unmuted and stuttered for a minute, and he said, there is no 1 in 5 million. It's just 5 and 6 zeros. Now, this superficial glance at probability statistics does give us an important point, which is surface logical truth has got very little to do with probability statistics. We're going to spend a chunk of time here on the distribution as the measurement tool of probability. And we're going to go into the forest this time. I know you're tired of going into the weeds, so we'll go to the forest. For the moment, we all are pretty good at some measurement tools, inches and miles, or its metric versions, pounds and tons, ounces, pints, quarts, their metric versions. We're familiar with these. We may not be particularly facile with all of them, but we grasp how they work in their relationship. We've got very little everyday experience or proficiency in the math of probability theory. We need probability theory to allow us to compare the sample data to a described distribution to estimate an outcome. Most common statistics used here in these examples and audits are point estimates, a type of mean, and confidence levels, the measure of the distribution around the mean. So these are the measurement tools of probability statistics, the mean and the distribution. For an example here, I don't have a pointer, but the green line is your frame, and the line in the middle is your mean. The samples, possible samples that can be selected, we're going to go from right to left. Possible samples could be selected randomly from this frame. Could be the one on the far right, which is skewed. It's got a big hump on the left, and the mean is just offset to the right a little bit. You've got the next one over is quite peaked. It's quite pointed and skinny, and the mean is right in the middle of it. It's not skewed. It's pretty good. But the mean is far from the mean of the true mean of the frame, not as far as the first sample. Third sample's in there in the middle. The mean's quite close, but the distribution is flat and low. And for the fourth sample on the left-hand side, you get a distribution that looks just exactly like your frame, but the mean is a long way away. What probability statistics does is tells you in each of these samples, their shapes and distributions and means are what predict the outcome of the extrapolation from the frame. All of these are legitimate. Probability statistics don't tell you, well, let me say it another way. The measurement question here is how accurate is the mean and the shape of each of these four as an estimator of the frame. It is the question and the only question that probability statistics can answer. Now, how accurate the mean is at estimating the true mean of the frame, probability statistics don't tell you the birth date of an individual. They don't tell you who's going to be president, and they don't tell you the dollar amount of the overpayment. They give you the likelihood that a chosen sample accurately estimates the actual overpayment of the mean 90% of the time. You could easily say, well, that's not good enough. Unfortunately, there's nothing more, and that's only if it's properly executed. So the verbiage here gets into back into the forest. We're going to talk a little bit about how things get made up in the central limit theorem, which is perhaps the key assumption of the statistics used in these audits. Within all of those possible samples that you can have with the number of samples in the number of claims in a frame, a mean can be calculated for each sample. Each sample mean would not be exactly the same value as most of the others. Rather, the means would differ from one another and they'd differ from the true mean of the frame. The means would be different from one another, however, they'd cluster around the central value of the frame. There will be more mean scores in the middle of the distribution than at its ends. And the difference between the means of the different samples are the basis for what we call sampling error of measurement. If repeated random samples are taken moving toward infinity or toward the total number possible in the frame, then their means would be expected to follow along a normal distribution. Now, that's way deep into the forest. What does it mean about meeting the probability criteria? What do you know about the fit of the sample of overpayments to the frame distribution of overpayments? You must know the assumptions of your methodology, your simple sample. You must know the assumptions of your statistic, and you must test to see that they're met. When the assumptions are not met, the audit is unlikely to give you an accurate measurement, the same thing that one would have gotten if you had audited every claim in the frame. The other day I was looking to find some brain teasers to help some ninth graders understand probability, and I was struck by how many of the examples called the students to look at the very same concepts that we're struggling with in these audits. The math gets lost in the verbal justification, and it used to be routine in Medicare audits that you would see, we say this number is the demand amount for a 90% confidence level. But because we only use the lower half, we're 95% confident that this answer is true. And it's just wrong. It's utter nonsense. They've stopped doing that, which is why I could use it as an example, but it really is troublesome. This is what's the big deal about the normal distribution? Why do we have to care so much about it? I'm going to cover this content looking at this graphic. Somewhere back in your class experience, most of you have had to learn something about the normal distribution, the bell shape, the Gaussian distribution, all different names for the same thing. It contains some assumptions that are essential for using parametric statistics like the ones that we use in these audits. When standardized, 68.27% of the elements will fit inside one standard deviation. So you look at what's in the middle and you see 34 and 34, and that's where you get to your 68%. Two standard deviations cover 95% of the data available, 3 standard deviations, 99.73. So you're less than 3.3% of the distribution, if it's normal, will lie outside the 3rd standard deviation. Now, the distribution is symmetrical. That is, if you fold it along the mean, which it will fold and be equal on both sides, so it's symmetrical. The mean, to remember, is an arithmetic average. The median, the other one that would be right there on that line, is the middlemost number, and that's the claim amount of which 50% of the claims will be above and 50% will be below. And the mode is the most frequent number that shows up in the distribution. And so when you have a normal distribution, the mean, median, and mode are all the same number. The normal distribution is the yardstick critically important to the functionality because it's a basis of creating the confidence levels, and the lower confidence level is the demand amount. So it is by far the most common yardstick used with a continuous distribution like dollars. And if the mean overpayment of the sample is a random variable, it can be expected that the confidence levels can be calculated mathematically. All of this weed stuff is what statistics can tell you. So how do we translate the weed stuff into something that's more meaningful to the provider? A 90% confidence level, 2 tails, means that you have one confidence level at the top in the tail and one confidence level on the right and one confidence level on the left. In continuous dollars, it would be the top dollar amounts on the right and the bottom dollar amounts on the left. So you'll have 5% of your confidence at the top and 5 at the bottom. And the 90% of the time, the sample overpayment of the mean will be between those 2 confidence levels if it's correctly calculated. If overpayment data are normally distributed, the sample mean can be used to calculate, and we can be confident that it's going to be a good measure of the mean of the frame, of the overpayments in the frame. Confidence levels tell you that if you look at 100 samples, 90 of them are going to be accurate, which means 10 of them are going to be inaccurate. That's the expectation. So we have to test to make sure we're working with the 90% or the 9 out of 10. Our discussion of distributions, point estimates, confidence levels, we've discussed a lot of ifs. If this were necessary, if that is met. If all of the ifs are not present, then your confidence interval statistic is not believable. So what if the distribution is not normal? This is an illustration based on made-up data. It's not accurate. The data are not real. It's for illustration only. But what you see here is the 3 measures of central tendency, the mean, median, and mode, which are supposed to be in one place, are all over the place. So where would you put your confidence level around the mean? The mean, of course, is $1,274. The most frequent amount, the mode, is way off to the left around 0. So 0 overpayments, meaning there were a lot of correct payments in this theoretical example. And the overpayment in the middle, at the 50% range, is $556. Then you've got some very high dollar claims off to the right that are going to raise the mean and distort the distribution even further. And the distortion and the impact of those, it's very tricky. And you can calculate a number, but it's not going to be an accurate statistic. 2 things you have to remember about what gets measured in overpayments. When you take the random sample, the amount that the sample is selected on dollar amounts, and the values amount for the amount paid. The overpayment isn't known until the sample is audited. Statistics require that the normal distribution be at the overpayment amount. So they are the criteria for using parametric statistics, or the confidence levels are destroyed. The second thing worth remembering is if overpayments don't correlate with the amount paid, then you should not proceed. And that was what Mr. Ross was talking about a little earlier. If the claims in error are greater than 50% in the 2019 MPIM, then you shouldn't extrapolate. If the dollar amounts in error are very small compared to the dollar amounts paid, you're not going to get an accurate estimation. It's just a bad plan. So you shouldn't do it. And it's not because the MPIM says you shouldn't do it. It's because statistically you get a bad number. We know it in advance. So let's look here at some real payments, some real dollar amounts. And this is an overpayment distribution. And I'm sorry, I don't have my pointer. The sample mean plus or minus one standard deviation. I'm doing this just because we can do it by arithmetic. So the mean is $430, and your standard deviation is 525. You immediately say, that's no good. When your variance, when your distribution of your variance, when the spread of your distribution is larger than your mean, you're going to get an inaccurate measurement. So if you add plus or minus, what you have here, sorry, I should explain the graph. You have on the x-axis, on the bottom, it's dollars, and on the y-axis, it's the number of claims at that dollar amount, and then there's a normal distribution superimposed over this data set. And what you see here is in the middle, where you should have a mean, median, and mode, you don't have much of anything. So your mean, your mean is not going to be a good estimator here. And if you go to the left, we're only looking at one standard deviation, not just over two. Your level where your overpayment demand amount would come is off the chart, indicating that it's an underpayment. So if it were a normal distribution, the theory says you will have an underpayment from this example. Normality is a big deal for overpayments. If a lot of claims are allowed, then there are a bunch of zeros with no overpayment. It's not bell-shaped. What's in the middle is problematic, where the mean, median, and mode should be. And then you have things off to the right-hand side inflating what the mean should be, making it not only not normal, it's an inverted. It's U-shaped, right? You've got a big high thing around $0, empty down to the bottom, and then it goes up a little bit, or maybe J-shaped, if not U-shaped. It's not a normal distribution. So knowing that the central limit theorem is the basis for how we make these decisions, and knowing that this data set happens to be very highly statistically not normal at 0.000, less than 1 in 1,000 measures of any of it would turn up normal. You don't have what you need to make extrapolation. Parametric statistics estimations in this case are no better than a guess. Dewey didn't win the election, and a baby isn't born on the date you assigned according to your theory. 90% confidence of estimate of this overpayment is not worth a hill of beans. I apologize that this stuff is really very hard, and I know we've been in the weeds for a while and been in the forest for a while, and there should be a pot of gold or a leprechaun here somewhere, but we're going to forge on with sample size. As David indicated earlier, sample size does matter, and saying it's not large enough doesn't get it done. But the question is it large enough to assert a 90% confidence level, and is it large enough to be the mathematical basis for an extrapolation? You'll hear that external factors may be considered relative to sample size. While it's true that external factors may be considered, you still have to have enough in the sample size to assert a 90% confidence level, and this has to be done mathematically. Go here to a representative sample. The sample has to be large enough to be a small and complete and accurate picture of the data in the frame. It has to be statistically accurate as a subset and reflect the numerical relationship of the entire frame and its distribution. A representative sample has to be unbiased, indicating exactly what it was like in the frame. The representativeness and bias has to be mathematically tested. When a sample is not representative, when the sample doesn't look like the frame, the result is unknown sampling error. In our example here, we have an iceberg, boat, ocean, and sky. And our good example is a small and accurate reflection of all of those. But if you come up with a sample of the boat and a little bit of selected sky and a little bit of selected water, and a tiny, tiny little bit of iceberg, it's not representative and it's not going to be a good measure. Now, one way to increase accuracy and decrease sample size is that you can stratify. You can say you're only going to take, in stratum 1, you're only going to do iceberg. In stratum 2, you're only going to do water. In stratum 3, you're only going to do you're only going to do sky. And in stratum 4, you're only going to do boat. And then you take simple samples within them, and you can be a lot more accurate if you have a simple sample within each stratum that is representative. But what if you only wanted to do the boat? All right, so you come to your frame. You can't randomly select the boat. So now you have to define a subsample, randomly select from the boat, and make your extrapolation. But you can only extrapolate over the boat. You can't extrapolate over the whole thing. If you weren't asleep by now, this ought to do it. I won't read it. David told me if I read this, he was going to go to sleep. What we have here is the math for choosing a sample size. And at the top, we've got the Greek formula. This sample is from RATStats, which is the OIG program. This one is the Sample Determination Program. It's based on the work of William Cochrane, who is a highly recognized thought leader in statistics in the 20th century. So it's a standard formula for continuous variables. So the top line, as I say, is Greek. The middle line is the same thing in plain words. And the bottom line is what you have when you have a 10% precision and a 90% confidence. And you fill in the blanks of the rest of those numbers. Now, RATStats is a really quite easy-to-use program. You start out with your universe or frame size. They're interchangeable here. An anticipated error rate of 10%. You get any level of confidence, well, any of those, all 4 of those confidence levels. You can get all 6 of those precision levels. You have to put in the total dollar amount of the frame and the standard deviation in the frame. And you get to choose how you do your output. And sure enough, it will give you confidence levels at a specific percentage. No one size fits all. And I was looking at a Medicaid case this week where the auditor used a sample size of 137 when this formula required nearly 3,000 claims to assert a 95% confidence level. Asserting such was indefensible. There was no mathematical basis to attain it. And it verbally claimed that it had met the requirements of a sample size that was 50 times too small. So that's no. Sample size matters. So we're now in the midst of a coronavirus where you're hearing about vaccine studies, and the numbers are huge, and this is taken from one currently being done. And what you have, we're going to start at the top, randomized numbers of 30,000 people, split equally into a vaccine group and a placebo group at 15,000 each. Now, the reason they anticipated that, the reason that number was chosen is because the anticipated infection rate is 1%. So they wanted 150 people infected in the placebo group. Then they wanted 150 people infected in the vaccine group. And in the vaccine group, there were 87 people protected, and there were 63 people not protected, which gives you an effectiveness rate of the vaccine of 58%. So in order to find out that 87 people could get protected in a randomized design, 30,000 people is the sample size required. Now, you can't say, well, that's a lot of people. We don't really want to know that. We just want to say the effective rate's 58%. Well, I'm sure people will say that. I'm going to move on to precision versus accuracy, and I'm going to go to the example here while I'm covering this slide. Precision measures how often a measurement tool produces a similar result every time it's used. Accuracy is how close the sample value comes to the true value you're trying to measure. So how close the sample overpayment mean is to the true mean of the frame. So up here we have, on the upper right-hand side, we have 5 really tight samples, and they're very, very precise, but they're a long way from the center of the bullseye, which is our accurate point. On the left-hand side, we have 5 that are not very tight. They're less precise than what was in the upper right-hand side, but they're still a good way from even the bullseye, much less the center of the bullseye. So they're neither precise nor accurate. And then we've got 5 in there that are in the bullseye, but they're very spread apart. So they're not very precise, but they're fairly accurate. Samples can be accurate and not precise, precise and not accurate. Extrapolation requires that they be both. And as you saw, the way we use precision is different in statistics than the way it's commonly used. So let's have an example here. If a random sample of 5 of the top most expensive claims, and there are the numbers, produce a mean of 5,555, and we have a frame of 100 claims that range from 500 to 5,570, the mean is 2,827. Now the precision here is going to be very small, and they're going to be very tight, but the point estimate is going to be nearly twice as large as the frame. The sample mean is twice as much as the frame. So the precision is going to be good, but the accuracy will not. So a point estimate this kind of point estimate can actually exceed the amount paid, and we do see this sometimes, that the point estimate is greater than the amount paid. Well, that can't be. It's a bad estimate. The second example, we're going to start kind of at the bottom, second from the bottom row. You have a random sample of 5 that selects the 2 top claims and the 3 bottom claims, and their average is 2,539. Where you see the frame average remains 2,827. So the precision, because you go from the top to the bottom, precision is going to be very, very large, meaning bad, and the confidence levels are going to be very large, and maybe send the lower confidence level into negative territory. But the point estimate is going to be pretty close to the frame mean. So the precision is unacceptable, but the accuracy may be okay. The lower confidence level may be a number. It's a bad estimate and should not be used. So a little bit more into the forest for the calculation of precision. And again, it's a calculation, so it's not going to, it doesn't fit what we want it to say in the words. If I say I have a precise measure, it just means it's a reliable measure. It does the same thing time and time again. So the point estimate plus or minus the precision amount gives you the confidence level. Precision amount divided by the point estimate gives you the precision percent, which is the number we talk about most frequently. The accuracy of the method is somewhere between the top and the bottom confidence level around the point estimate. Lower confidence level is as close as any number that can be attained for an accurate overpayment. So when you hear someone say, we give you the benefit of the doubt because we use the lower number, it's just nonsense. So the formula, we talked about the point estimate being the mean overpayment times the frame size, and then here you have your chosen confidence level divided by 2 for a two-sided, and that's just the formula. You put the same numbers into the same formula, you will get the same output every time. Now, to show the problem here with getting the same answer every time, I created a file of 1, 2, 3, and so on to 150, and I labeled it overpayments. Then I dumped that into RATstats, a variable appraisal program, with a frame size of 20,915. And here are the completely bogus outcomes. So a sample size of 150, there were no non-zero claims. That means there were no claims that were correctly paid, and the value of the sample was $11,000. Frame 20,915 means their standard deviation. The point estimate's 1,579,083, and the confidence level of no meaning at all is 41,456. And so you put garbage in, and you will get garbage out. This sample of overpayments was not random, not normally distributed, not representative, not independent, not a probability sample, and not big enough to assert a 90% confidence level. So the overpayment calculator expects this to be true, that there's a probability sample with every one of the 6 steps there, that there is a parametric statistic for point estimates and confidence levels that have a random sample, independent observations, normally distributed sample averages, and is representative, and that there is an adequate sample size. We'll go through the probability sample last because it will be the last mind bender I do to you. So you remember the possibility to calculate the number of samples of a given size given the frame. We spent time on that. And it has to have a known probability of selection. Those are the 2 biggies. And you have to properly execute the parametric methodology, which with all those 4 steps. You must use proper randomization. And that means if you have dependent data, you use different output than if you have independent data. You have to use the correct formula for calculation. And as you saw, whenever I put things that violated all of these tenets into RATstats, it promptly gave me a $41 million overpayment estimate. Much of what we're looking at is not much better than that. So often we don't have proper randomization for independent samples. We don't use the correct formula, and therefore, not surprisingly, we don't get accurate estimate overpayment measures. Sample size, I think we've beaten pretty well. So now I had initially intended to use this as an example for questions, but I do want you to pause for a moment and let this information sink in. But I also think that this picture is a really good example of how we on the statistics end view the outcome of what we've just talked about for the last several minutes. And we see it as a big picture. We see it as its complexity is necessary. And then you all have to ask questions of us that are linear, that fit into regs and the law as you understand it. And you also have to get us to make that picture verbal. And we're not very good at it. And it is one of the things, well, I'm going to say I'm not very good at it. We do talk among ourselves that it's hard for all of us. But that's what you need your expert to do for you. I want to make a couple of overall statements. As counsel, these cases have the opportunity for you to help your clients become good consumers of statistics at the higher levels, well out of the weeds. The providers have to demonstrate that the audit was invalid, thus documentation is essential, and good documentation, not just provided early on, is essential for figuring out whether these key components are met. The higher level comprehension of that it's not right, what I'm saying is not right, is key to your understanding, because you have to trust your gut on the higher level stuff. Sometimes we'll come back to you and say, no, that just doesn't work that way in probability statistics. But if you can't grasp the higher level, if we can't explain to you the higher level issues in such a way that you can explain to the judge, then we on the expert end are not doing our job. You all are really good at solid legal logic and at constructing arguments. And while it's hard to put a picture into words, you're as good at it as anybody there is. And to ask us what the 3 most important ideas are and how that translates into your argument. We stat folks are not good at making those kind of priorities, but the parts are equally essential to you for making your arguments. Currently, I find that Medicare and Medicaid contractors, including Medicare reviewers, are stuck on a one-size-fits-all, hammer this into, and trust me, I said it, it's right. They gloss over very complex statistical standards required for estimation, and when that's the case, the statistics are invalid, or if they're improperly executed, they really should be challenged. And the only amounts paid that should happen in those kinds of audits where the extrapolation is bad is the amount of overpayment in the sample itself. So that's pretty much where we are now. I think we're ready.
Thank you very much, both there. Yeah, thank you, both our speakers, for your insights today. Before we move on to Q&A from our audience, I do have a brief announcement. So that New York and Kansas states require you record and report the following code to obtain CLE credits for the live or recorded version of the CLE webinar. If you will be requesting CLE credits for the seminar, please write this code down. Code is TLGHCP. That's T like Tango, L like Lima, G like Golf, H like Hotel, C like Charlie, and P like Peter. Again, that is TLGHCP. Now we move on to our live question and answer session, where our listeners can ask our speakers any questions relevant to today's topic. You may email questions to healthlaw@straffordpub.com or submit questions by typing your question into the Q&A box at the right side of the screen and press enter. We can start with a couple of questions we've been submitted through here. Do you have an example of a time when the Medicare error rate was less than 50%, and what was the result in that case?
Sure. We've had one case where it was somewhere in the low 40% error rate, and we had a hearing, and the decision after the hearing, we won a few more claims, which lowered the percentage a little bit more. And the result was the audit contractor determined that the sample disallowances that remained after the hearing would not be extrapolated because they were pretty far below the 50% threshold. And like I said before, it's not a requirement that if they don't have a 50% threshold, they can't extrapolate. There are other factors that they can bring to bear that would justify them. None of those particular factors were present in our case. So we went from a demand amount well in excess of $700,000 to, I believe, somewhere $33,000, $36,000, something like that. So that was a significant victory. I think without those changes to the MPIM in January 19 effective date, that wouldn't have happened. So yes, these things do happen, and that it is the light at the end of the tunnel. When if you're close to that threshold, your goal may be less than totally taking the castle. You may just be able to whittle your disallowances down to a point where they won't be extrapolated. But like I said, it's not a guarantee. It's not a requirement that CMS has imposed on themselves. It's just another option becomes available that they can select. So I don't know if you want to add anything to that, Dr. Mikus.
We've seen it both in extrapolation and in voluntary repayment cases, and I think it's equally important in both to be able to say. And some of the voluntary repayment cases, the numbers were down in the 10 and 20% range, and so they really never should have been extrapolated. And it gave a good reason for, frankly, if they had done a probe or they used their sample as a probe, they would have known not to do a larger extrapolation sample. I've seen it in a couple of the other side of it, and sometimes you hear that Medicaid entities don't want to adhere to the MPIM, saying that, it's not a state regulation and it's required. But the point of, for me, the point of the change once I came to terms with it was that when it said a prior error rate of magnitude, they were talking about a time when the amounts paid really did correlate with the amounts overpaid, and when you or the number of claims in error was very close to 100%. Statistics work less well the lower down those things get, and it shows up in your precision percents.
That's great. Thank you so much. Another question there is, what is a stratum and when is stratification used?
Strata are subsets of the frame, right? And you break it, often they're broken into ascending levels. And the intent of stratification is to take something that has wide variance and to chop it into smaller pieces with smaller variance in order to reduce the sample size and increase the accuracy of estimation. There's a pretty good fight afield right now as to whether, because those, let's say there are dollar strata that go in $20,000 increments, and there are 5 of them. And when you get to the one that's $100,000 and above, if you put zero, if you end up with a chunk of 0 overpayments, now your strata goes from the very smallest, covers all that's in between in the overpayment, to the very largest. So I'm not exactly sure that there's a statistically sound way to do stratification here at the moment. If it is, I'm not seeing it being done with that level of sophistication.
Well, Pat, if I could add, we have seen cases with stratification. We've handled them 4 or 5 different strata. And is it true to say that that means there needs to be 4 or 5 simple random samples, one for each strata, which needs to follow all the rules that you've espoused?
That's correct. Each stratum is its own simple sample, and they all have to be, overpayments have to be normally distributed, and they have to be random, and they can't have the same seed and all the rest of those sorts of things that are really quite complicated. In a simple sample, you just multiply it times 4 or 5. But you can use a smaller sample size.
Okay.
Great. Thank you both there. Another question is, if you have an example of an effective argument that catches the judge's attention about issues with the sampling and extrapolation process.
Sure. I mean, we've seen several. One, issues regarding the adequacy or accuracy of the universe as it's claimed to be as provided by the auditors. Sometimes they're described in such a manner that suggests that there's an apple and orange problem, as Pat indicated. We've seen instances where claims were in the sample. That means they were supposedly in the frame from which the sample was derived, which by the audit definition could not possibly have been in the frame, because I think one of the examples Dr. Makefield mentioned was providers being included in the frame who, in one case, didn't work at the clinic or did not submit claims during the time period. And the only way to detect things like that is to go through the claims, and it's very time-consuming, very laborious. Sample size, unless you can show some dramatic decrease in, the precision of the audit, the judges, I think, because they hear that so frequently or relatively frequently, that's not super effective. But you never know what's going to catch their eye. And we had a recent hearing where I think it was just a matter of bias in that the sample was overrepresentative in that it contained too many high-dollar claims than one would expect. I say too many, a disproportionate percent of claims in the sample that was indicated because in the universe they had, a far lower incidence. So that was something that really shaped the hearing almost from the outset of the expert's testimony. So things like that are attractive, and if your case has them, you want to lead with things like that. The more obvious to a layperson the problem is, like, why does this sample contain 70% high dollar claims? That's something that is something you can go with, and even a lay judge, can pick up on that, particularly the Medicare judges, who tend to be pretty sophisticated in their approach to these issues because they've heard them for years. So I don't know if you have other experiences, Dr. Mayku?
Yes, I think the most frequent reason for a withdrawal, that where the auditor withdraws or it gets thrown out, or for there to be a settlement based on just the amount paid, is documentation. If you can show that the provider did not give the basis to defend itself, if there's no random sample, I've had it thrown out, there's no universe, or there are multiple universes, or failure to produce the overpayment data that match the demand amount, those sorts of things, those are not statistical errors, those are just not producing errors, and judges really do grasp them.
Great, thank you so much again. And another question, are you able to cross-examine the Medicare contractor's statistical expert?
Well, curiously enough, under the CFR, these folks do not appear normally as parties. So they are what are called non-party witnesses. And non-party witnesses give sworn testimony. The judge asks questions. The appellant is prohibited from asking questions, even direct questions. I mean, this person would not ever be your witness. But you're not able, as a rule, to cross-examine non-party witnesses. So they tend to appear in that manner, I believe, at least in part for that reason. And I did a hearing fairly recently where the contractor's expert finished and the judge said, "Mr. Ross, you're a witness." And I had to scramble because I didn't expect it. There was really no regulatory basis for it. I guess anything is at the judge's discretion. And I quickly rebounded, and it was quite a damaging cross-examination, in my opinion, not just because I did it, but because of the answers that were elicited, and they essentially wound up, it was a short-lived experience because the judge terminated the cross-examination before too much time had passed. So you're not entitled to it. You may get it on a surprise basis. It's a question you may want to ask ahead of time, but there's no regulatory authority for it, so it's really in the judge's discretion.
Thank you. I'm guessing there's a follow-on. Sorry, please go ahead, Dr. Mayku.
I had the experience where the judge turned to me and said, "Is there anything you want to ask the other side?" And was not as dexterous as Mr. Roth. I did not come back very quickly with it, but I have been prepared for that since.
Yeah, the judge is free to ask any witness anything, so you have to be ready for a curveball, particularly if there's some novel issue in dispute. The judge may want to hear, from your expert. Without you, there's not going to be any redirect examination, but the judge can say, well, to the appellant, well, let's ask your expert what they think of that. So it's not cross-examination per se, but at least the other side of the coin, can be displayed for the judge to see.
There's one question that came in here on the audience-enabled
Yeah, another question there. If you've ever seen one of the audits done correctly without any fatal flaws.
I certainly have, and they're when they follow on my next the slide before the picture of questions, when those 6 things of a probability sample are met, and when the 4 things of the parametric statistic are met, and they have adequate sample size. I mean, really what we're saying, and I think everybody believes, that we can measure Medicare overpayments. We can measure Medicaid overpayments. We just need to do it properly and follow where the data goes, not what's easy to plug into a computer program.
So let me answer that. I do primarily New York State Medicaid defense work, quite a bit of Medicare, but in terms of sheer numbers, New York State Medicaid, and we see the same sample size in virtually every case. So every case sort of starts out flawed in that respect because they never seem to achieve a large enough sample size to get their confidence interval, at least as they express it. So they're all flawed in that sense, and experts can differ about this. Are they fatal flaws for having an inadequate sample size? There's some debate about this, that just per se having a small sample size is not going to push you over the line, particularly in Medicare audits. But if you can show, how bad that sample is in terms of size and the consequences, the collateral consequences of choosing a sample that small, you might get there in Medicare. But the extrapolation based on, this stratification business, I've never seen one done correctly. I mean, almost laughably incorrectly. And for someone like me who, to laugh at the lack of competence of some of these auditors, really, it's got to be pretty extreme case. But the non-stratified ones, I mean, you wind up sometimes in these debates with your expert, okay, the confidence interval might be 88%, or is 70 or 87.8%. Is that close enough to 90% under the MPIN? Is it close enough? I don't know. Is it close enough for government work is the joke, right? So it's flawed, but is that the kind of thing the judge is going to say it's fatally flawed? And the one time I encountered that, perilously close to 90% deficiency, we're waiting for the decision on. So I don't know how that judge is going to rule, but these things are not terribly difficult to do correctly. I think when you have complex universes, widely varying claim amounts, multiple providers, different reasons that would throw a wrench into the process, that's where you're going to see, in my opinion, a higher likelihood of a fatal flaw, or more than one, actually.
I think what you just said there, David, is a very important discussion. The hardest thing to do in any of these, whether you're designing them or reviewing them, is to design the question such that it's statistically answerable, not just take what's convenient in your data set and throw it against the wall and see what sticks. I mean, if there's time spent, and the new MPIM is heavy on the design, and even if you're using it repeatedly, if you put your time in there and find out what you have, and then you build your statistic based on what the data tell you in the frame, this is not all that hard. It can be done. But it's not a one-size-fits-all, throw it against the wall, see what sticks.
Great, thank you both there. We've got one last question, and that is, as a statistical expert, how can an attorney help make your job as an expert easier?
I appreciate that question because we are very much, as my last illustration showed, we're very much in our own world, and we think all the puzzle pieces are equally important, and that's really not productive to a good testimony. And so for those attorneys that spend the time to understand some of just the basic things of statistics that need to be there for statistics to work, the probability space and the random number piece, then they can begin to say, that's very interesting, but I can't make that work in this case. What else you got? And you will then come with 4 or 5 things that will come to fit, because they're all equally important on the statistical end, because you have to have the whole picture without a hole in it. It's not the same with complex linear logic. And so it can be very helpful when they just say backward to us, that one can't fly this time. So rethink it, find another way to say it, but as you're presenting it, it just sounds like mothballs.
Right. Did you have anything to add there, David?
In terms of what I would look for in an expert, somebody who will spend time with me and go through, every stone, turn over every stone, so that when we're evaluating the case, I have a conversation with the client about how to proceed, whether to proceed, whether to settle, that sort of thing. Somebody who just covers all the bases, doesn't talk too terribly far over my head. I'm sure they will talk over my head, but that's all right. They're experts, and we understand that. Someone who has experience, who's frankly seen it all or seen almost all of it. There are surprises, but that's what I look for in an expert. It's less about where somebody went to school, but it's more about how they communicate. They're going to be a good witness, at a hearing. Virtually all of the Medicare hearings are done over the telephone. They don't have a visual component. You can request a video conference, but they're very expensive. They foot the bill, and right away you sort of start off on the wrong foot with something like that. So you want somebody who enjoys the work. I mean, that there's a lot of intellectual challenges and activity going on in these audits, and like I said before, that Medicaid Fraud Control Unit toolkit, you read that and you see all the decision points and how easy it is to sort of take the wrong path, to go down a road that you shouldn't go down if you're an auditor. And you want somebody who can say, yep, that's where they took the wrong turn. I think when you have that, you do the best you possibly can for your client. Hopefully you get an outcome that they can live with.
That's great. Thank you both again. That brings us to the end. We hope you've enjoyed the national webinar, Medicare and Medicaid Audit Overpayments, Challenging Statistical Sampling and Extrapolation. If you have questions that were not answered, you may email these directly to our presenters. Their email addresses are included in the presentation. If you are seeking continuing education credit, you must verify your participation in this webinar by completing and submitting the attendance affirmation evaluation after the program. A link to this form will be included in the thank you email that you receive immediately following the program. If you have paid and registered by 5 p.m. today, you receive your certificate of attendance within 24 hours. If you have any questions about the continuing education credit, please call the Continuing Education Department at 404-881-1141, extension 2. Today's participants can order a recorded version of this event at a special attendee price. Please call customer service at 800-926-7926, extension 1, or visit Stratford's website at www.stratfordpub.com. If you are not yet a Stratford Annual Pass holder, you may try the CLE Individual Annual Pass. You can get all your CLE credits for one low price. Simply respond to the email you receive after the program. Stratford would like to thank you for your attendance today. To end this call, simply close your browser. Thank you and goodbye.